Hello everyone and welcome back to Math Made Easy. In our previous lectures, we completed the first derivative using the forward difference, central difference and the backward difference formulas. But in numerical and differentiation, it is not limited to finding only the first derivative. What if we need this f double dash x, the second derivative, or even the higher derivatives as f triple dash x, f fourth x, and that's what we are going to study in today's lecture. We will derive the second derivative formulas using the finite differences, understand the forward, backward, and central forms, discuss their accuracy, and hence solve the numerical examples. So before going into the numerical formulas, let's just understand the terminology. The first derivative is here, this f dash, which is defined as this df over dx, and the second derivative as f double dash as d2f over dx2, and this third derivative this d cube f over dx3, and fourth derivative as d4f by dx4. So in numerical differentiation, we can approximate these derivatives using the function values in a finite difference table. So let's just start with the most important formulas as the central difference formula for the second derivative. So consider the Taylor expansion around this xi, where this f of xi plus h equals to fxi plus h times f dash xi plus h by 2 factorial f double dash xi plus h cube by 3 factorial f triple dash xi plus h power 4 by 4 factorial f4 xi and so on. And this f xi minus h becomes fxi minus h times f dash xi h square by 2 factorial f double dash xi minus h cube by 3 factorial f triple dash xi plus h power 4 by 4 factorial f4 xi and so on. Now just adding these two equations, the first derivative terms cancel and third derivative terms also got cancelled. So we get this fxi plus h plus fxi minus h as twice of fxi plus h square f double dash xi plus h power 4 by 12 f4 xi up to so on. Therefore, this f double dash xi becomes f of xi plus h minus twice of fxi plus fxi minus h divided by h square minus h square by 12 f4 xi and so on. Now just ignoring the higher order terms, so we get this f double dash xi is approximately equals to fxi plus h minus twice of fxi plus fxi minus h divided by h square. And this is a central difference formula for the second derivative. Now let's just rewrite it in finite difference notation. So we have this fi as fxi, then this f double dash xi becomes approximately fi plus 1 minus twice of fi plus fi minus 1 divided by h square. And this is one of the most important formulas in numerical differentiation. Now just notice the pattern as this 1, minus 2 and 1. So a quick way to remember it is the next value minus twice times the current value plus previous value all divided by h square. So from our derivations, the first neglected term is actually containing this h square. So therefore, this truncation error becomes this order of h square. So the central difference formula for the second derivative is second order accurate. And that means if we reduce this h, the truncation error decreases approximately proportional to h square. So assuming the other sources of numerical error remains controlled. Now let's just derive the forward difference formula for the second derivative. So we can use the forward difference operator here. Now just recall this delta fi equals to fi plus 1 minus fi. And the second forward difference is delta square fi equals to delta of delta fi. Therefore, this delta square fi equals to fi plus 2 minus twice of fi plus 1 plus fi. So for the equally spaced data, we have this f double dash xi approximately delta square fi divided by h square. Or explicitly we can approximate it to fi plus 2 minus twice of fi plus 1 plus fi divided by h square. And the truncation error of this basic forward formula is order of h. So it is first order accurate. Similarly, using the backward difference operator, this nabla fi becomes this fi minus 1. And the second backward difference is nabla square fi equals to fi minus twice of fi minus 1 plus fi minus 2. Therefore, this f double dash xi is approximately equals to nabla square fi divided by h square, and hence approximate to fi minus twice of fi minus 1 plus fi minus 2 divided by h square. And again, this backward formula has truncation error as its order of h. So just like the first derivative, the location of the required point helps us to choose the formula. If it is near the beginning, then you need to use the forward difference formula. If it is at an interior point, then use the central difference formula. If it is near the end, then use the backward difference formula. So, and this simple rule will help you choose the appropriate formula quickly in an examination. Now we have a quick question where we have given this tabulated data as its x values as 1.9, 2 and 2.1, and this fx as 6.6859, 7.3891 and 8.662. So we need to find this f double dash 2 using the central difference formula. So we need to calculate this f double dash 2. That means this since this 2 is an interior point, so we can use the central difference formula here. Firstly, we have this h as 2.1 minus 2 as 0.1. So our formula becomes as f double dash xi approximately fi plus 1 minus twice of fi plus fi minus 1 divided by h square. Therefore, the f double dash 2 as f of 2.1 minus twice of f2 plus f at 1.9 divided by 0.1 whole square. Now just substituting the values, so we get this 8.1662 minus 2 times 7.3891 plus 6.6859 divided by 0.01. So we get this answer as 0.0739 divided by 0.01, and hence approximate to 7.39. So our numerical approximation for the second derivative is approximately hence 7.39. Now what about this third and fourth derivatives? The same finite difference idea can be extended to higher derivatives as well. For example, the third forward difference is as this delta cubed fi equals to f of I plus 3 minus thrice of fi plus 2 plus 3 times fi plus 1 minus fi. So our basic approximation for the third derivative is f triple dash xi approximately equals to delta cube fi divided by h cube. That hence ultimately becomes as fi plus 3 minus thrice of fi plus 2 plus thrice of fi plus 1 minus fi divided by h cube. And similarly, this fourth forward difference is as delta power 4 fi equals to fi plus 4 minus 4 times fi plus 3 plus 6 times fi plus 2 minus 4 times fi plus 1 plus fi. And therefore this f4xi approximately becomes delta power 4 fi divided by h power 4. So the important pattern becomes is if it is nth derivative, then it will be the nth finite difference, and if it is nth finite difference, then it will be the nth derivative for sure, with the factor h in the denominator for the basic forward difference approximation. Now let's just make one distinction very clear. When we say higher order derivative, we mean derivative as f double dash, triple dash, or fourth. So don't confuse this with the order of accuracy, where this for example, if I have this f double dash xi as fi plus 1 minus twice of fi plus fi minus 1 divided by h square, which is a second derivative, but its truncation error is basically order of h square. So the two have in completely different meanings, and the second derivative tells us like which derivative we are actually calculating, and this order of h square tells us the accuracy of the approximation. So this distinction is very important. And that brings us to the end of this higher order derivatives. So today we learned how to calculate the second derivatives using the forward, central, and backward differences, derive the important central formula, compare their accuracy, and briefly extended the concept to third and fourth derivatives. So in the next lecture, we will move forward to the derivatives at unequally spaced data, where the usual equally spaced finite difference formulas can't be applied directly. So if this lecture helped you, please like the video, subscribe to MathMadeEasy, and I'll see you in the next lecture.